Thanks for inviting me, Sissy and others who are organizers. As Sissy mentioned, I am a computational social scientist. I work at the intersection of AI and society with a focus on language and language technologies, but drawing on theories and methodologies from social linguistics, computational other computational processing technologies or methodologies such as machine learning. Um, and currently, as I work as a senior research scientist at Google Research in the Responsible AI and Human-Centered Technologies organization, where I look at issues around fairness, transparency, accountability, and so on as it relates to the topic of AI and society. In particular, I focus on natural language processing. Today, my talk is titled NLP and Society, Undesirable Societal Biases as Barriers to Those in the Margins. So let me start with one of the fundamental questions when it comes to machine learning-based applications in general and NLP in particular. How can computers learn from data? This forms one of the foundational questions in the last couple of decades, I would say, when it comes to language processing technologies in particular. And these NLP applications, and especially powerful techniques such as word embeddings and contextual embeddings, such as BERT, GPT-2, some of these terms you may have heard about. And if you're familiar if you're working in NLP, you definitely have heard about these technologies or this infrastructure, these models. But even in popular media, these terms or these technologies have been covered a lot lately. The core sort of idea here is that these are models that have or that learn how to represent or learn some sort of representation of meanings of words based on where they occur in data. Right, and these are like some infographics that shows like how some of these technologies have learned meaning. But an important question here to ask is data a reliable representation of, is the data that we use to train these models a reliable representation of the world we want to model? So I will start with a quick exercise here. What do you see in this slide? If you've already seen these slides, please please don't respond. But if anyone who have not seen the slides would like to volunteer one or two answers, please unmute yourself and answer. What do you see in this figure? Any answers?
You may not be able to unmute yourself, but if you raise your hand, we can give you permission to unmute yourself. You can add your answers in the chat. Oh, I see an answer in the chat.
I think I see the answers coming through. Bananas. Okay. Okay. I forgot about the fact that like people can't unmute. So I'll go ahead. So as in the previous iterations of this talk, when I've asked, some of the common questions or common answers I've gotten is bananas, stickers, people who recognize the stickers there, doll bananas, people who are familiar with the sticker or the brand, bananas at a store, bananas on shelves, bunches of bananas. But I don't get the answer yellow bananas. People don't usually say yellow bananas when they see this figure. In contrast, if you see a picture like this, you're more likely to say green bananas or unripe bananas. We don't usually say yellow bananas because yellow is often perceived as prototypical for bananas. And this happens not just in the context of bananas, it happens in other contexts too. For instance, we are more likely to call out the gender of a doctor when we are referring to a female doctor. In the case of male doctors, people often do not specify the gender, since oftentimes, or for a large majority of our society, male gender is sort of prototypical or perceived as prototypical for the doctor occupation. And this can be seen by a simple web search. This is like screenshots that I've taken a few years ago, but I don't think the numbers have changed significantly or flipped over the last few years. These results, the number of the female doctor, the search for female doctor as a quote, occurs more than twice as often as male doctor in articles indexed by Google, for instance. This prototypical association is also documented in a large-scale study conducted by Boston University in 2014 as well. So all these are examples of sort of what is called human reporting biases. That is, the frequency with which people write or talk about actions, outcomes, and properties is not really a reflection of the degree to which a property is characteristic of a class of individuals. You could think of a property as a characteristic of certain kinds of objects as well. So this kind of brings back to the question of like, is data a reliable representation of the world you want to model? So if the data that is out there is not going to be characteristic, if that's not going to capture the characteristics of certain objects and certain individuals or sets of individuals, then is it okay, or is it okay to learn understanding of meaning from that data through automatic means? And so that was one kind of biases. There are all sorts of other kinds of biases that occur in data. For instance, selection bias, that most web-based data suffer from huge gender bias in terms of who authors this text. Men are overrepresented in web-based news articles. Men are overrepresented in Twitter conversations. There's also significant gender bias in Wikipedia and other encyclopedic repositories, language repositories out there, which forms the basis for training large models like in recent years anyway. Moving over from like, who has authored the text or authored the language data, moving over to who we typically recruit to annotate the data. Most often crowdsourced annotation platforms do not have a globally representative annotator pools due to various factors. This is a screenshot from a few years ago again. This was a map of Amazon Mechanical Turk workers. As you can see, there are like certain hubs from where people or annotators come from. And this is something that we all kind of recognize as a bias that exists. But as a result, the people and their perceptions and their cultural competences or cultural exposure or familiarity with cultures like do affect like the labels that we get. For instance, in this particular, this is like an example taken from an image captioning data set where the first two images, all three images are of wedding or some wedding function, whereas the first two were annotated as ceremony, wedding, bride, and so on. The last one was annotated as just people or person. Most likely because the annotators were not familiar with the cultural sort of cultural knowledge that the last image is an image of wedding. So is data a reliable representation of the world you want to model? Maybe not. Now, why does it matter? In one of the early studies in NLP on this topic, Bolog-Bassi et al. Showed how the underlying representations of meaning representations that the word embeddings or these sort of like large models or large sort of meaning representations capture stereotypes that exist in society and maybe even perpetuate those stereotypes. For instance, they found that in those meaning representations, the relationship between man and a computer programmer is similar to a woman and a homemaker. And that kind of gave rise to a lot of work in the space on fairness or unfairness in NLP models. Since 2016, publishing this work in 2016, there has been, I would say, even hundreds of papers working on various kinds of biases or working on demonstrating various kinds of biases, as well as attempting to mitigate them. But this is not just a matter of what is represented in these meaning representations, right? Like these would have similar or such biases have downstream impacts on allocations of resources, for instance. If you're using AI tools or NLP tools in areas where allocations of resources are determined by that model or influenced by that model. In a few years ago, a hiring tool that was used by Amazon was shown to be penalizing resumes that has the word women's, an association that puts female job applicants at a disadvantage, since the word is very likely referring to, things like women's soccer team or women's tennis and so on. And finally, another example that I'll talk about is toxicity classifier, or any sort of like online content moderation tool that uses the NLP technology to remove offensive content. Uh, so a specific example that I use here is Perspective API, which is used to perform online content moderation, and it is used by various large platforms in different ways to moderate their content. It may not always be censoring the content. It may be about routing the content to human review and so on. So, the effect or the downstream impact might differ. But it was shown that a naively trained model that is used in one of the early versions of this Perspective API had strong unintended biases towards certain identity terms, especially LGBTQ terms and certain religious terms. For instance, the sentence, "The gay and lesbian film festival starts today," was labeled as toxic, with a score of 0.8. This is a score that varies from 0 to 1. This work was done by Jigsaw, the sister company of Google, who build the Perspective API. So they themselves found these biases and talked about these biases and has since mitigated them. But that is just like one kind of biases, and there's still a lot more research going on in understanding and mitigating various issues like this. But the point here is that here, for instance, the terms gay and lesbian might have this strong association, strong negative or toxicity association, because the data that the model has learned from probably comes from online social forums where the terms gay and lesbian are more predominantly used as an abuse, as saying "Oh, you're so gay," or "That's so gay," or some sort of usages where the word is more often used as a derogatory term. And that is the meaning that the model has learned. So as a quick stop here to sort of say NLP-based abusive language detection is an example kind of use case that I'll be using throughout the talk. So I wanted to, not all of them would be about Jigsaw's Perspective API per se, but most of the work I'll now be presenting is on fairness failures or fairness issues in the task of abusive language detection. Because I'll be using the toxicity classification often, I want to just sort of set sort of like a or a shared definition of what toxicity means in this context. Here, Jigsaw defines toxicity as rude, disrespectful, or unreasonable comment that is likely to make you leave a discussion. I do want to note that this is not the only way to think about toxicity. There are many other definitions people have come up with in recent years, looking at abusive behavior online. And the idea of toxicity, this is more defined from the perspective of a platform who is trying to sort of make a space that is safe for everyone. But if you ask the same, ask to define toxicity to a user or a community or a person belonging to a marginalized community, they might define toxicity very differently. So that's an important aspect to take into consideration while we go through this talk. But because most of the work that I'll be presenting uses the idea of toxicity or data annotations of toxicity using this definition, I wanted to sort of set that stage first. So I'll start with this sort of this figure, which I'll keep coming back to, where, the very basic schematics here of most often the machine learning models that we use currently are built using a neural network that automatically learns the concept you're trying to teach it by looking for patterns in data and updating the weights between those neurons or layers according to how those patterns are associated with the concept you're modeling. So here I have shown a two small layer network just as a sort of like a demonstration. But these models nowadays go up to billions of parameters, right? And there is the data, and that data is fed into like this modeling sort of step where these patterns are looked into, and like these weights are updated. And I'll start by looking at some of the biased predictions, right? We talked about this example of toxicity classification, and how mentions of LGBTQI terms or religious terms tend to have show these biases in predictions. Now, in 2019, our team looked at what biases exist in the models around specific people. Because these people are likely mentioned in data a lot, what has the models learned about them? That was a question that we were asking there. Turns out that just by changing the name from Katy Perry to Taylor Swift, a sentence turns from non-toxic to toxic, or sentence turns non-toxic. That is, if you consider a threshold of 0.75, which is a common threshold used in various contexts as a toxicity threshold for this model. So this is kind of interesting, but also, like as I said, it might be because these are, these individuals are mentioned a lot in online social media and have sort of the models have sort of like attributed certain meaning to these words, these names, and that may have toxicity associations. And this analysis contained like all sorts of different names, including like politician names, and you yourself can actually try this model if you're curious about certain names that you care about. But in that work, our focus was, can we have a more generic methodology to detect such biases in models? So with my colleagues, Ben Hutchinson and Margaret Mitchell, we looked at, or we introduced this idea of perturbation sensitivity analysis to detect unintended model biases. And this is in line with many other work like that are also coming out in the same time. Like it's very related to what you might have come across as counterfactual fairness evaluation work. This is like one kind of counterfactual that like leans on a specific sort of idea. So the idea here is simple. We use a target corpus and extract a small number of naturally occurring sentences, as opposed to like templated sentences, or like sort of like small set of like template sentences that is often used in fairness research. But we extract a small number of naturally occurring sentences from that target corpus, and then identify what we call an anchor point, where things that are semantically similar, such as names of people or names of places, can be swapped in and out or perturbed. We can then run these set of perturbed sentences through a classifier to see and to do more statistically statistical analysis to demonstrate if there is like systematic biases around certain names or certain groups of names and so on. So the idea is very simple here. In this particular work, where we wanted to like look at biases around certain names, certain person names, we use pronouns as the anchor point, because with simple rules we can replace a pronoun in a sentence with a name while keeping the syntactic structure of the sentence more or less valid. There might still be edge cases where the semantics would get a little bit tangled up, but that is not really a problem in the context of this evaluation where you're looking at biases in the models. So first, doesn't matter, does perturbations result in switching toxicity labels at a chosen threshold? In our analysis, we found that, say, at a threshold of 0.8 to be considered toxic, 35% of the sentences labeled as toxic flip to non-toxic just by changing a name. Almost the same percentage of new sentences were flipped to toxic just by changing the name. So that is a problematic sort of scenario where a model is so unstable that like the prediction of something is toxic or non-toxic is so dependent on like the mentions of or names that are mentioned in the sentence. Switching labels, this happens across different thresholds. It was not just happening at the threshold of zero point 0.8. Across different thresholds, this kind of behavior was happening, but at different rates. Now, in follow-up work, we were looking at, could this be used to detect biases around groups of people? This is work, again, done in collaboration, led by my colleague, Ben Hutchinson, and in collaboration with my colleagues, Emily Denton, Kelly Webster, Yu Zong, and Stephen Dinio. Here we use this perturbation sensitivity analysis as well as some other analysis to look for social biases in NLP models as barriers for persons with disabilities. It was one of the axes that was not studied up until then in the fairness community. Here again, like as a demonstration of this issue, as a starting point, if this model was given the sentence, I am a person, I am a tall person, it has very low toxicity score, close to 0. If I say I'm a blind person or I'm a deaf person, the toxicity score goes up to 0.39 or 0.44. If I say I'm a person with mental illness, that even goes further to 0.62. So these are very simple sentences, or like, with neutral sort of valence, and so there's no reason for these to be labeled as toxic. So you could imagine how a borderline sentences might actually are more likely to be labeled as toxic, just because of the presence of certain mentions of disabilities, right? So we applied the same perturbation sensitivity analysis here on a large set of sentences, but instead of names, we used mentions of people with disabilities as the perturbation candidate. We curated a list of and for that, for the mentions of disabilities itself, rather than using like some ad hoc set of mentions or like disability names terms, we curated a list of recommended and non-recommended ways to refer to people with disabilities based on various resources that are out there, such as SIG-Access, ADA National Network, and Anti-Defamation League. So these resources also distinguishes recommended ways to refer to people with disabilities as well as non-recommended ways. We found that compared to the baseline, mentions of disability increased the chances of sentences being flagged as toxic. This was the hypothesis that we had started with, and also was what was demonstrated in the previous table. And often, non-recommended ways of referring to people with disabilities, such expressions produced higher model scores than the recommended ones. So that's a very good thing, very good sign that the model still recognizes, or model predictions still adheres to the fact that the non-recommended or model scores are still making like higher scores or higher toxicity scores for if the input contained non-recommended ways to refer to people with disabilities. So that was a good sign. But still, even just a recommended way to refer to a person with disability, or even mention of disability, was causing models to sort of like be more likely to produce a toxicity score that was higher. Now we go look at biased representation. So I alluded to the representation of biases like in one of the slides earlier. Here we looked at biases that are that may have been captured around mentions of disabilities, or like the meaning of the word, meaning of certain of these terms, to see if there is like what sort of associations it has captured. So there's many different ways of analyzing these representational biases. In this work, we looked at, we probed this language model called BERT, which is a very popular kind of base model that is used for most modern NLP applications in the last 4 or 5 years. And there's a lot of variants of like BERT, like Albert and Distilbert, and all sorts of different versions of BERT, but also other BERT like, or like, advancements over BERT like GPT-2 and so on, which are all about contextual word representations. So in this work, we probed BERT. This was work done at the time when BERT was the kind of state of the art, sort of, to discover what words it associated with disability. So the way we did that is similar to perturbation analysis, but like slightly different analysis here. We start with sentences that had a mention of disability, and the way the BERT model is trained, and so usually used to probe as well, is fill in the blank task. Like, so is through a fill in the blank task. So you provide the model with a sentence where like one word is removed, and then see what that word. The idea is that the model has a representation of language good enough that it can actually fill that blank with like something that is appropriate, right? So here we start probing the model with a large set of these templates that we built that has the mentions of disabilities, and looked at what was the word that was introduced by, or like that was predicted by BERT. And then we ran it through a sentiment analysis model. That sentiment analysis is also an NLP model. It may have biases around disability. So in order to control for that, we used the different template, which is just like a neutral template, which does not have any other context, like a person is that word. That's how we control for that. And then we looked at how often are these predicted words labeled or deemed as negative by the sentiment model. And turns out that mentions of disability on average increases or is more likely to predict or come up with, or sorry, the BERT model is more likely to come up with negative sentiment words if probed with sentences that contained mentions of disabilities. Now, the next question we asked is, where could these biases be coming from? So one obvious place is data, human biases that are captured in data that are then coming through biased representations and then going to models, right? So first we looked at societal biases that are captured in the source data, the language that is used to train these models. Even for this analysis, it was also part of this paper where we used a specific data set, which was built by the Jigsaw team for unintended biases in toxicity classification. So they had a Kaggle competition where they released a data set. A subset of the comments in that data set have been labeled with a variety of identity attributes representing the identities that are mentioned in the comment, of which the identity term of, or like the disability mention of mental illness was had over 5,000 instances. So we specifically focused in this analysis mentions um, mentions of mental illness or that subset of data. And this corpus, perhaps unsurprisingly, we found that the mentions of mental health were more likely to co-occur with medical topics such as medication and diagnosis, or towards the left. The first two columns are, terms that are more associated with the condition or the treatment, right? However, if you look at towards the right, like the rightmost association, the mentions of mental illness in the basic in the core underlying data set had more association with terms such as terms or topics such as homelessness, drug abuse, and gun violence. So if you think about it, these are not necessarily stereotypes. I mean, depending on how you define stereotypes, these are also part of like public discourse around mental illness. When people talk about gun violence, people often evoke the mental illness as an issue. When people talk about homelessness, there is an overlap with mental illness in terms of like who is affected. So all of that might be playing into these associations, but nonetheless, these associations do exist in data and hence are more likely to be captured in the models that are trained and as are resulting in predictions, right? Now, the next source of biases that we look at is human biases in annotations. So here, this is ongoing work, some of which is already accepted, or already published, where this is led by my intern, Aida Davani, and in collaboration with my colleague, Mark Diaz. These work, the first one is published at Tackle earlier this year, and the second paper was published at a workshop last year at EMNLP. So here we look at the common practice of obtaining ground truth annotations that are used to train our models. In most cases, especially if the data is collected through crowdsourced annotation platforms such as Amazon Mechanical Turk, we obtain annotations or labels from several different annotators on the same instance, sometimes 3, sometimes 10, depending on how much money you have or funds you have. And most often we aggregate them using a majority vote or just present an average score or distribution across the labels. Rarely, when it is feasible, some studies do some sort of adjudication as well when there is disagreement. But in all these approaches, we are chasing a single ground truth because we need that to train our NLP models. However, in the case of subjective tasks, there may not be such a single ground truth. And this is an idea that has been very eloquently put by Sisi's early work, I believe from 2011 at EMNLP, which basically makes this point. But we continue to do as a community, collect these multiple labels and get a single ground truth by taking majority vote, which is not really an appropriate thing to do. Or at least that's what we try to do or try to demonstrate in this work empirically. So first we ask the question, does aggregated data uniformly capture all annotators' perspectives? For this, we analyzed 3 different data sets annotated with 8 different subjective concepts, 6 different emotions from an Go Emotions dataset, and then sentiment and hate speech. For some tasks, as marked with the green circles in the bottom left and right for especially, most annotators had pretty high agreement with majority labels. The agreement score is the kappa score that is on the x-axis, and the number of annotators who had that level of agreement with the final majority vote is in the y-axis. So as you can see, for tasks such as joy and even for hate speech in this particular data set, had pretty good agreement of 0.6 to 0.8, which is really high agreement in some cases. However, for some other tasks, such as annotating disgust, fear, and sentiment, this is not the case. This has not been the case in these data sets. A substantial percentage of annotators' perspectives were not at all reflected in the majority labels. It could be that those were noisy annotations, but we argue that these are also there might be systematic ways that annotators might disagree on these subjective tasks that are derived from their own socio-demographic backgrounds and lived experiences, right? And another factor here is that it is the same set of annotators who annotated the discussed data as well as the joy data, right? So it's not the case that it's all noisy annotators. Some of these tasks, some of these concepts may have more variability depending on annotators' backgrounds. So specifically, we asked whether the disaggregate or aggregated data reflects certain socio-demographic groups' perspectives more than others. For this, we could do the analysis only on the sentiment data set that was released by DS et al., who did collect the socio-demographic information associated with annotators, because their work's main focus was to understand the annotator bias. So they had a really rich data or this metadata about the annotators so that they could study. The focus of their study was age bias, but they also had other sorts of metadata about the annotators. So here we looked at gender, ideological differences, as well as racial differences, racial identity. Turns out that not all groups' perspectives were equally represented in the majority label. While there was no significant difference along the binary gender axis, which was captured in the data, as I said, the majority labels had significantly lower agreement with annotators who identified as Black compared to those who identified as white or Asian. Now, this is a more important, there's a very very important point here. This sort of disparity is different from what is usually entirely in data, right? This is not a disparity that is created. This is not a disparity that is just because there is disparity in the data, and that's usually like an excuse, almost like the machine learning researchers and developers give, saying that, oh, society is biased, so the biases are reflected in data, right? This is a particular case where, like, it's not just a society, or it's not just that, like, the biases existed in the data. This is that we or the researchers, or like, if you are taking a majority vote, you are creating this disparity by taking a majority vote while you have like a smaller number of participants from a particular community, and thereby marginalizing their perspectives, right? So in this particular data set, that they didn't use this to train any models, so that was not the case. But like, if you do majority vote, it has a potential for introducing new biases into your pipeline. So what do we do? So I'll briefly talk about some work that we did in terms of like how to sort of account for it, rather than mitigating it, like account for different perspectives in the modeling stage. In the tackle paper that I talked about earlier, we proposed a multitask architecture, a multitask approach to predict individual annotators, keeping their own perspectives as like a valid representation of that task, while keeping a shared representation of the task that is shared across all the annotator models. So we could do this multi-annotator model in many different ways. So we experimented with like 3 different approaches. The first one on this image here on the left is a baseline, where there's like, you take the majority vote upfront, and then you train a model using that majority vote, and make the predictions. But in all the other settings, you are actually predicting separate annotators differently or separately, either as an ensemble of separate models. You could think of it as like a multi-label annotation task, or you could use this multitask annotation task. Like, I invite you to check the paper for more details. In interest of time, I wouldn't go into the details here. But the multitask model, as I said earlier, it learns these representations for these multiple annotators' perspectives as separate classification tasks, but also sharing the encoder layers that has the same representation of the input sentence. And one of the first advantages of this is that it gives you a sense, or it gives you an ability to model uncertainty at the prediction time, right? So when it gives you an ability to say that, oh, this is an input sentence where annotators may have disagreed. And that's an important insight to know at prediction time for whoever is deploying it into the system, into socio-technical systems, could then like use that as an insight to sort of route those sentences for additional review, with this additional category, additional insight that this was somewhere like the model suggested like there is a high uncertainty, as in multiple annotators may have differed on this particular input. Uncertainty modeling is a completely different line of research that has been going on for decades. And there's even within machine learning, or within the neural net approaches, there are approaches to calculating uncertainty, such as doing using the softmax of the prediction, as well as like a Monte Carlo approach, using dropout, sort of like repeat dropout kind of approach. So we compared our approach with these like other models of like looking at uncertainty. And turns out that our way of modeling uncertainty using this multi-annotator model obtains a significantly more correlation with the disagreement that was demonstrated between annotators compared to softmax and MC dropout based approaches. This uncertainty is not just, we also found that the uncertainty calculated by such multi-annotator models varies across different types of erroneous predictions, such that on average, incorrect predictions of the multi-annotator model have higher uncertainty than correct prediction. That's this may not be transferable to other tasks, but like at least at the training level we can actually know these factors that actually can then be used in when you're deploying models in the real world. um, and also in this particular task, when looking into specific types of errors, we found that the model is almost always certain about true negatives and uncertain about false positives. In other words, high uncertainty in multi-annotator prediction can likely indicate false negative and false positives. So that's an interesting extra info. I mean, it could also be used in like making the final prediction more programmatically. Um, so the next question we asked, does this hurt the predictive performance or time complexity? We compare the multi-annotator model to the baselines on a hate speech detection task, which was also used in the previous slides. And we found that like the performances in this particular task, that the performance of the multitask model is ever so slightly even better than predicting the majority label. So if that is what you really want, the majority label, it actually does a better job of predicting that than the baseline approach. There's reasoning for why that might be happening that I invite you to read the paper for that, or I can answer during the discussion. It also doesn't add a lot of time complexity to the prediction task. The baseline model, the single task model, took 20.5 minutes to train in one of those cross-validation experiments, whereas the multitask model took 22.3 minutes. So it's like 2 minutes extra in this kind of setting. It's like a 10% improvement, increase in time. So in closing, I talk about the various ways in which human biases enter the data and the modeling stage. So not just the data, like, in the modeling decisions, like, how you choose the threshold, how you choose to aggregate labels, all of that affect the biases in predictions made by the model. But one thing that in my work and in my team's work, we are very particular about, or we look into, is the fact that the biases do not just creep into these model, into this systems just based on like data. There are biases that are creeping into the model at the deployment stage. Human biases in like modeling stage would also go into like how things are deployed. But there's also biases that like shape how you define problems. As I was talking earlier about how you define toxicity, that was like the toxicity data that is out there, and a lot of like data work, NLP work, uses that data, and that data uses a definition of toxicity from a particular point of view, a point of view of a platform. That may not be the most useful way to think about toxicity or online abuse for a society at large, right? So there are biases in like even how we define the problems, and we do look at, like, in some of our other work, like we do look at that sort of questions as well. And human biases in deployment as well. And in a longer term, these biases have a potential to sort of result in changing the data that is out there in the world, and like having a feedback loop. For instance, some of these biases, as you were probably, if you're familiar with NLP, there's a lot of language generation models that are out there in the last couple of years, which can generate very natural looking language examples. And if they are being created by like language models that are biased, may have stereotypes, may perpetuate stereotypes, 6 years, 7 years down the line, when a machine learning model is trained using data from the web, it doesn't really know how to distinguish like what was the data created by humans and what was the data created by models. And so there is this likelihood of like things being amplified or things being sort of like propagated in and like having a feedback loop there. So Margaret Mitchell, my ex colleague, labeled this term as a bias laundering, which is like this idea of like bias being sort of like laundered through this pipeline. So this points to the fact that like we have to find a way to model societal context, accounting for its dynamically complex nature and feedback loops and delayed impacts and emergent properties if we want to meaningfully intervene in fairness based issues in NLP and AI models. So while most of the work that I presented here in this paper, sorry, in this talk, kind of attack or looks into the data and model kind of considerations, we also, our team also have a lot of work in the broader ecosystem or fairness interventions or fairness work or research in the broader ecosystem. For instance, participatory approaches to fairness and using community-based system dynamics points to the need for sort of participatory problem formulation. So this is work led by Donald Martin and many other colleagues within Google externally, as well as like at DeepMind. And we also have work led by Nitya Sambashivan, my ex-colleague, who led this work on sort of like looking at some of the core assumptions on fairness work, which is largely situated in the Western context, looking for biases in the Western public discourse or biases that are prevalent in the Western public discourse, and how these assumptions or this research may not be portable to other sociocultural or geocultural contexts. So specifically in this work, reimagining ML fairness in the Indian context. So in closing, this is a saying that I really like of my colleague Donald Martin Jr. That there is a crisis in AI around ethics, and it is not really a crisis in the public understanding of science, but rather a crisis in science's understanding of the public. With that, I will close, and I'm ready for questions.